Hello everyone, and welcome back to another Calculus 2 video. In this video we are going to talk about trigonometric integrals, and we're going to see some techniques to help us integrate. With these types of problems, usually what's going to happen is we're going to have a mix of trig integrals. Maybe we have sine cubed times cosine x, or maybe we have something that we're integrating sine squared of x, in which case we're going to have to use a power reducing formula. Some of these are going to require substitutions from all those trig functions that you had talked about before. So everything starts with this Pythagorean identity, sine squared plus cosine squared is equal to 1. We know that we could take this and we could rewrite it into 1 plus cotan squared of x is equal to cosecant squared of x. We would get that if we divide everything by sine squared. So that's another Pythagorean identity, which is really a manipulation of this one. Or if we divide this by cosine squared, sine squared over cosine squared is tangent squared, plus 1 is equal to 1 over cosine squared, which is secant squared. So in some of these problems, we may have to make a substitution for a sine squared, rewriting this as 1 minus cosine squared, or maybe even a substitution for one of these other trig functions. So we could come up with some guidelines, and these are some possibilities that may work for you. This is not a definite, if this happens, then always do this. Once you get to higher level math, those if this then that doesn't necessarily always work. It just depends on the problem. But let's say we have an odd number of sines, then maybe we can convert some of those sines to cosines, depending on what we have, reserving a sine so that we could do a u substitution once we expand everything out. So you can see how we would rewrite that sine squared as 1 minus cosine squared, coming from that Pythagorean identity, making that substitution, and then multiplying everything through so that we could do some u subs. If our cosine, the number of cosines we have is odd, and notice the stuff is multiplied together, then we could do the same kind of thing, converting some stuff to sines using that same Pythagorean identity, solving it for cosine squared. That would be equal to 1 minus sine squared, and then multiplying through. If we're integrating just a sine squared or a cosine squared, we could use what's called a power reducing formula. And these are formulas that are on our cheat sheet on that trig side that you may end up needing to use. Other things you may end up needing to use would be product to sum or sum to product formulas. So let's look at a few examples with sines and cosines. Let's say we want to integrate cosine to the 8th of x times sine of x dx. We're going to think about a u substitution here. So notice I've got 8 of those cosines and only 1 sine, so I can go straight to that u substitution. Same thing that we've really been doing since Calc 1. U is going to be cosine of x. The derivative of cosine is negative sine of x. So we would need a negative 1 here and compensate with a negative out here. And we took that derivative with respect to x. So if we did our rewrite step, it would be negative integral of u to the 8th times du. And then when we integrate that, we're going to get negative u to the 9 over 9 plus c. And when we substitute back in, it's going to be negative 1/9 cosine to the 9th of x plus c. So there's our final answer. Now let's say we change that problem slightly and we're integrating cosine to the 8th of x, but now instead of just 1 sine, maybe we have a sine cubed. So we have an odd number of sines here. So you can see how we're going to rewrite that sine cubed. We could think about it as a sine squared times sine. So let me write that. And the reason I would want to do that is because I can make a substitution for that sine squared. I know sine squared plus cosine squared is equal to 1. So sine squared is equal to 1 minus cosine squared. So we're going to make that substitution for that sine squared, reserving one of those sines. And then I'm going to do some fancy math, and I'm going to distribute. So I'm going to have cosine to the 8th of x times sine of x minus cosine to the 10th of x times sine of x dx. And now I'm doing a u substitution for each of those. To do that, I am going to have to rewrite this. Split it into two integrals. Minus cosine to the 10th of x sine of x dx. We know u is going to be sine, so du is negative sine. So we need a negative 1 here, compensate with a negative here. Same thing here, negative 1, compensate with a negative. Notice that minus negative there. So when we integrate, and I am not going to write out that u substitution since we just did that on that problem, I would add 1 to the exponent, divide by the new exponent. That minus negative becomes a plus. I would add 1 to the exponent, divide by the new exponent, and then we're going to have plus c on it. So there's our antiderivative, but you can see how that changed because we had more signs than what we had before. So we had to use a Pythagorean identity to convert there. Let's look at another one. Let's say we want to integrate sine cubed of 4 theta times the square root of cosine of 4 theta d theta. So it'd be nice if we could reserve one of these signs, because I can't really do a lot with this since it's under the radical. So let's do a rewrite here. We're going to reserve a sign, and that's going to leave us with a sine squared. Let me clean up my square root there. Now, this guy is the same thing as 1 minus cosine squared of 4 theta times sine of 4 theta times, and this is really cosine to the 1/2 of 4 theta d theta. So we're going to distribute everything into this parentheses. So 1 times that stuff is going to be that stuff. Sine of 4 theta cosine to the 1/2 of 4 theta d theta. And if I distribute here, minus, I'm doing 2 steps in once, distributing and rewriting as 2 separate integrals. This is going to be cosine, and I have these two that I'm combining, so that's going to be a total of 5/2 of 4 theta times sine of 4 theta d theta. So let's think about our u substitutions here. I'm going to do this off to the side here. If u is cosine of 4 theta, then du, derivative of cosine, is negative sine. But then we have to take the derivative of the angle, which is 4. So you can see how this is going to become part of that du. So I'm going to rewrite that step, and I'm going to cheat a little bit and use my technology to let me rewrite this a little quicker than just literally rewriting. Copy, paste, Now all I'm going to do is change the order of that first one. So this is going to say cosine to the 1/2 of 4 theta times sine of 4 theta d theta. So we're using that u substitution. So notice we need a 4. So we need a 4 here, compensate with a 1/4. It's actually a -4 and a -1/4. Same thing here, -4, compensate with a -1/4. So we're going to have -1/4, and we're going to add 1 to the exponent. So adding 1 to 1/2 is going to give me a 3/2. And then I would divide by the 3/2, which is the same thing as multiplying by the reciprocal 2/3. Over here, this would be plus 1/4. Same thing, I'm going to add 1 to the exponent, so that's now going to be a 7/2. Now I'm going to divide by 7/2, which is the same thing as multiplying by the reciprocal. 2/7, and then plus c. So you see how we did that u substitution? And then we're going to reduce these fractions. This is going to be -1/6 cosine to the 3/2 times 4 theta plus 1/14 cosine to the 7/2 of 4 theta plus c. It looks like I forgot my complete sentence here. Don't forget that argument of the trig function. So let's look at one more. What if we're integrating? Maybe this is a definite integral. Let's do one of those. 0 to pi over 2. This is going to be cosine to the 5th of x dx. So here's the way I would see this. I'm going to rewrite this cosine to the 5th as cosine squared times cosine squared times cosine. So that's going to reserve a cosine. I can convert these to sines using that Pythagorean identity. Sine squared plus cosine squared is equal to 1. So cosine squared is equal to 1 minus sine squared. So this is 1 minus sine squared. This is 1 minus sine squared. This is cosine. And now let's multiply everything out. So if I multiply these two together, it's going to be 1 minus 2 sine squared x plus sine to the 4th of x. And that needs to be multiplied by cosine of x. So that's going to be cosine of x minus 2 sine squared times cosine plus sine to the 4th times cosine. So let's look at the big picture here. If we're thinking about substitutions, we're going to do a u substitution here and here. U would be sine of x. The derivative of sine is cosine of x. So let's integrate. If I integrate cosine, I'm going to get sine. When I integrate here, that cosine is my du, and u is sine. So when I integrate, I'm going to add 1 to the exponent, divide by the new exponent, and then same thing here. This is part of du. So I'm going to integrate, adding 1 to the exponent, divide by the new exponent. So there's my antiderivative, but we want a definite integral here. So we're going from 0 to pi over 2. So we're going to use that fundamental theorem of calculus. So it's going to be sine of pi over 2 minus 2/3 sine of pi over 2 cubed plus 1/5 sine of pi over 2 to the 5th minus, and then we're going to plug 0 in. Sine of 0 is 0. So this would be a 0 as well, and this would be a 0 as well. We know sine of pi over 2 is 1, so this is going to be 1 minus 2/3 times 1 plus 1/5 times 1. Which is going to be 8 over 15. So let's look at secants and tangents because we know there's a relationship there. If we have an even number of secants, then we can reserve a secant squared, make a substitution, and turn everything into tangents because we know the derivative of the tangent is secant squared. So the goal is to make u your tangent here. If we have an odd number of tangents, then we can reserve a secant tangent and try to turn everything into secants because we know the derivative of the secant, if that is our u, would be secant tangent. So let's look at some examples there. Let's say we want to integrate secant squared of x over 12 times tangent of x over 12 dx. So we could think about u being your secant. If that's u, the derivative of the secant would be secant tangent. So we could think about rewriting this as secant x over 12 times secant of x over 12 times tangent of x over 12 dx. So you can see how that's my u. That would be du, but don't forget we got to take the derivative of the angle, which is 1/12. So we are missing the 1 over 12. We can compensate as long as we multiply in a 12 somewhere else in the problem. Let me see if I can make that a little bit better. There we go. So this would be u. All of this gets absorbed inside of du. So when we do our rewrite, we're integrating 12 times the integral of secant of, oh, just kidding, that's u du. And then when we integrate, we're going to get u squared over 2 plus c. And then when we substitute back in, we're going to get 6 times secant squared of x over 12 plus c. So there's their final answer. Let's look at another one. Oh, I'm trying to add another page and it's not letting me do that for some reason. There it goes. Let's say we want to integrate tangent squared of x over secant of x dx. So I'm going to pull that 13 out. So I've got tangent squared over secant squared. It would be really nice if I could rewrite that tangent. We know there's a relationship, right? We talked about those Pythagorean identities before. We know 1 plus tangent squared is equal to secant squared. So that means tangent squared is equal to secant squared minus 1. So that's what we're substituting in for that tangent squared. And then now let's split that numerator and reduce. Secant squared divided by secant squared would just be a secant of x. And then we're going to have 1 over secant, which is the same thing as cosine of x, that we're going to integrate. So if we're looking at our formula sheet, if we integrate secant, we're going to get secant. Sorry, I was looking at the wrong formula. If we integrate secant, we're going to get ln of secant of x plus tangent of x. And then when we integrate cosine, we're going to get sine plus c. So there's our final answer for that one. So let's look at some other ones. Let's say we need to integrate something like cosine of 3x times cosine of 9x. Notice those have different arguments. So let's use one of the product to sum formulas. So if you're looking on your trig sheet, product to sum, there's one that says cosine u cosine v is equal to 1/2 times cosine of u minus v plus cosine of u plus v. So that's what we're going to use here. So we're going to rewrite this. So it's going to be 1/2, I'm going to pull that out, cosine of u minus v. So 3x minus 9x is a minus 6x plus cosine of u plus v. So if I add those together, I'm going to get 12x. So I'm going to think about integrating each piece separately. Let me give a little space here since we'll have to think about a u substitution. Dx plus. So if we're thinking about our u sub, we would need a -6 if this is u. This would be du. Here, u would be 12x. So du would be 12. So we would need to compensate with a 1 over 12 here and a -1 over 6 here. When I integrate cosine, I'm going to get sine. So I'm going to get sine squared of -6x over 2. And when I integrate cosine, I'm going to get sine here. Hold on a minute. What am I thinking? It has been a long day. When I integrate cosine, I'm going to get sine. And when I integrate cosine here, I'm going to get sine. So let's simplify. So this is going to be a -1 over 12 sine of -6x plus 1 over 24 sine of 12x plus c. We know sine is an odd function, which means I could think about that negative really being out here, which would make that a positive 1 over 12. sine of 6 times x plus 1 over 24 sine of 12x plus c. And let's do one more using a power reducing formula. Let's say we're integrating sine squared of x dx. Going back up here, we saw the introduction of the power reducing formulas here. We could rewrite that sine squared as 1 minus cosine 2x over 2. And then we're going to think about splitting that numerator. And then integrating each of those terms separately. I'm going to pull that 1/2 out. So this would be cosine of 2x dx. So when I integrate 1/2, I'm just going to get 1/2 x. This guy's going to require a u substitution. So we would need a 2 here, compensate with a 1/2 here. So that's going to give us a minus 1/4. Let me see if I can clean that up a little bit. So we had that 1/2. And then when I integrate cosine, I'm going to get sine plus c. So there's our final answer. Now, if you need to write the u substitutions out, that is perfectly fine. You can do that off to the side. You can do it below. But as you progress through this course, you're going to see that you're not going to need to write as many of them out. If I pull that 1/2 out, I would get cosine of 2x. So u would be 2x. du is 2 dx. You can see how we would need that 2 here. I'll put it out here and compensate with a 1/2 here. So that's where the red stuff came from. And then when we do our rewrite, we're going to have 1/4 the integral of cosine of u du. And when we integrate, we're going to get sine of u. And then when you substitute back in, you're going to have 1/4 sine of 2x. So you can see where that's coming from. So if you need to write them out, that's perfectly fine. Write them out. If you don't need to, that's okay too. In the next section, we're going to take trig integrals to a different level. We're actually going to use trig to help us solve different types of integrals.